And for now, we'll move on to our next talk in the session. This will be Menelaos Sarantos, Contributions of Volatiles to the Lunar Exo-ionosphere Using ARTEMIS Data.
Okay, are we online?
We hear you.
Can you hear me? Okay.
I think you hit the camera.
Yeah, we don't see you yet.
Is that the webcam? Oh, wow. Okay. And then
Okay,
we
coming
are.
through.
And then we need to share. Oh.
I think you're on.
Oh, we're on. Okay, and so you just Zoom next page like that. Okay.
Okay, great. Thank you so much. I apologize for the disruption. So, the title of the work implies that we would like to use ion data from ARTEMIS and with context from previous observations that had mass resolution to say something about undetected species of the exosphere, namely volatiles, mostly molecular ions. So, again, the idea is to introduce some new models of the exosphere, mainly species that we didn't study before, volatiles, and use ARTEMIS measurements to constrain some of these abundances. Again, the objective, the justification is this ion mass spectrometers could be much more sensitive than UV or neutral mass spectrometers. And the recent availability of ARTEMIS data really enables this work. In a series of papers last year, we presented a very thorough model for refractories in the gas phase. And there was a reason for this. They're really easier to model because you can very much assume that they just stick. So all you have to do, or one has to do, is quantify the production rates from solar wind sputtering and micrometeoroid impacts, and just track them under gravitational forces for the most part. With volatiles, the interaction with the soil is much more complicated, so we try to amend our previous model to capture some of the expected abundances. As before, the first step is really to thoroughly quantify the expected rates from the influx of these species, for example, carbon compounds, from both micrometeoroids and the solar wind. And Rosemary Killen in a previous presentation discussed some of that work and how we arrived at these rates. The second portion is really determining or deciding how to treat the interaction with the surface of the material in the gas phase that returns. And what we've done here is very simplistic. Just assume that on the day side nothing sticks, and on the night side everything sticks but the non-condensables, neon and helium and that sort of thing. However, we did not consider reintroducing in the simulation particles that fell on the night side and would stuck there. And as I'll show you, it looks like the ion measurements are telling us that this transport of volatile material from the day side to the night side and its re-emission on the day side, again, depending on some activation energy that's to be determined by experiments, is really important. Anyway, this is a thick plot, but basically, for example, if you look at the profiles for water, this is water from a global micrometeoroid impact source. And we estimate it to be about 100 to 500 per cc on the day side. Other things are evident here, for example, methane. If you convert all the amount of carbon in the solar wind to methane, it really doesn't amount to much because it's one of the short-lived molecules that get dissociated on the day side relatively quickly. So we would estimate maybe 30 per cc of this material on the day side. So again, this is just to estimate some order of magnitude densities and use them in conjunction with the existing ion measurements. Rosemary also showed this work, which is really the context from previous observations, ion mass spectrometers that had mass resolution. And so on the left, we have our previous model of refractors. This is just atomic species. Just assume that the exosphere consisted only of atomic neutrals. And on the left, this is our previous model with upper limits for things like carbon and sulfur pre-LRO. Surprising, I mean, when we started this work, our objective was really, this missing oxygen over here, and I guess I can't see my cursor here. Obviously, the measurements from WIN and AMTI showed high abundances, maybe even pronounced abundances of O+, something around mass 16, which we're not able to reproduce, assuming that atomic oxygen came from impacts and solar wind pattern. However, one could get a fairly good fit in the mass region between 20 and 35 based on atomic species. On the other hand, once one adopts the LRO new limits for things like sulfur, aluminum, silicon, and especially the very reduced limits for carbon and oxygen, even the very good fit in the 20 to 30 mass region goes away. And it looks like this old measurements, based on the spatial, on the instrument mass resolution, which was approximately 8, they really indicate additional channels around mass 28. Phosphorus was claimed as a detection, but what we really are saying is that it's impossible to explain these measurements with an exosphere that consists just of atoms. So what happens when you introduce a molecule to this picture? We use, for example, some scenarios here where we introduce carbon monoxide and dioxide to levels up to 500 per cc, methane 50 per cc, and water ranges between 500 to 2500 Kelvin. And you see that for the carbon molecules, given those assumptions, you really don't make a large change to the atomic, the spectrum expected from atomic species. But that is really to say that you can vary a lot of volatiles given this ion measurements. You could have significant, in the thousands, concentrations of volatiles without ever violating these measurements. For water, though, you kind of get a stronger limit. Anything more than 500 per cc really alters the measured spectrum, assuming that we now have, with LRO upper limits, we now have a relatively good absolute abundance range in the 20 to 30. And so we can use that as our standard candle for evaluating what the molecules should be adding to this system, how many molecular ions to get a fair fit. So we can do this in great detail from ARTEMIS, which of course, as Jasper Hallecker showed yesterday, detects pickup ions, very sharply focused, coming from specific directions. But the question is, of course, we don't have mass resolution, so we must rely on some sort of modeling in addition to using the direction of arrival at the instrument and the overall measured flux to determine what sort of mass compounds might be arriving. This is shown here in one simulation, one long interval. This is just a slide from a three-dimensional distribution. And you see flux for helium and sodium ions. And you see that depending, given where these ions were observed, the overall levels and the direction of arrival is far more likely to be sodium plus than helium. So we can use this type of turning of the trajectories to determine what these ions are. And so we simulate measurables by ARTEMIS, the energy spectra, and just to fast forward through this, essentially one can use the measured differential energy flux at the peak, shown here in black dotted lines, and the different models, co-add the different models using a penalized least squares formulation to infer the likely set of compounds that arrive into the instrument. What we're really interested in rather getting a unique solution, is really assessing the uncertainties of these derivations. And this is shown here in this figure. Basically, one way to do confidence limits is to add a little bit of noise to the objective function that you're inverting, and repeat, this is called the perturbation method, and repeat the solution 1,000 times. And so you get this nice histograms, if you wish, and what do we see? Well, for many of these species, our forward model, namely things like methane or NO or N2, our forward estimates, our expected estimates from the exosphere are consistent with what we derive from this data, namely particle expected concentrations in something like 20 per cc. See, everything is in the first bin there. For sodium, of course, we have detection, so we know what to expect. We infer something like 40 per cc here in a Gaussian distribution. We know from ground-based observations this to be about 70 per cc. Argon plus, argon 40 here is a good portion of the measurement, but we do find it to be reduced given the Apollo observations, and also about twice less than the LRO upper limit. So maybe this is, again, this is a consistent picture. CO, we think this is an important component in the mix. It's here in the thousands. We can't really reproduce it in the model at such high levels. It is the most, the longest-lived component of the carbon compounds. So we could put in something between, I think, 200 and 2,000 per cc in the forward model. Here we derive it to be somewhere between 2,000 and 4,000 per cc. Again, an acceptable solution. We think that there is O2 in there, and that would necessitate about 3% of all oxygen in micrometeoroid impacts to become O2, and this is consistent with some quenching theory calculations. Last, an important result here, I think it's a solid result. Neon is found to be here somewhere in the thousands, and this is at least 10 times less than our forward model estimated. And so this is actually telling us about 90% of helium, of neon, rather than being thermally re-emitted following saturation, is rather escaping. And so this might allude to results similar to Jason's. In other words, that maybe some of these heavy ions from the soil wind, heavily in the process of getting neutralized in the soil and charge exchanging, they really are emitted with far more energetic distributions from the surface than just thermal. And so these are my conclusions. I think from previous measurements, there could be a significant amount of volatiles around CO and extending all the way to argon-36. We see that in the ARTEMIS data, but it's more like an indirect derivation here. Jasper talked yesterday about how in the solar wind, all these mass peaks really line up between 20 and 40, line up at the same mass channel. Whereas in the magnetosheet, we have this new data set that really shows some separations and should make ion detections and derivations even more stringent. We do think that there's some significant results in these derivations, mainly the presence of CO perhaps in the thousands, even water, as you saw, where we were deriving thousands per cc, which were maybe a factor of 10 more than we anticipated on the base of the previous measurements. The source of observed O+ is still puzzling. We just can't explain it. A lot has to do with the breakup of these molecular ions in the foil. ARTEMIS wouldn't see that because it doesn't have a foil, and yet if we observe something around the O+ signature, especially if it's cold, like Jasper's papers suggest, it still remains, it's a part of the puzzle that still remains. So I will leave it at this.
If you have questions for Menelaos, please enter them into the chat. Just a quick question regarding the exospheric water abundance limits. They seem very consistent between your modeling and the LRO data. Can you say a word or two about how LADI might contribute to that understanding?
I mean, I don't want to speak for the LADI team. It's going to be a difficult measurement to make if it's in the hundreds. Maybe the water ions will be observable by UVS, and we intend to provide signal-to-noise estimates to the team for just that. Depending on the scale height of water, whether it's from impacts or whether it thermalizes, we may get some Z values because these ions get picked up. Depending on the scale height, we may have some shifts in and out of the center of the line, so we need to account for all this. This is still a work in progress.
Fair enough. We have another question from Jasper. Could the O plus actually be H2O plus? 2 AMU is not a big difference for many instruments.
I think all the previous measurements show mass 16. It is wider than their mass resolution would allow there. My own feeling is that we see the O plus from the from mainly the molecules. It doesn't quite line up at the O plus. It lines at because it doesn't have the same velocity. It lines up right next to it, left or right. It would give a broader distribution than just O plus. But I think a lot of this is just pure O plus, and we just can't anticipate why it's there. But even 10% breakup of these molecules in the foil will give you a lot of O plus, which I didn't include, by the way, in those figures. I think they look substantially better when you start adding the breakup of the molecular ions in the foil.
Great. Well, thank you. If there are